Hey calculus class, today you're going to learn topic 42, area between curves. So let's first think about it. Let's say we want to find the area between the curves of y equals x and y equals x squared from 0 to 1. So here I have my graph where the pink graph is y equals x and the green one is y equals x squared. I want to find the area between these two graphs. So that means I want this area right between the pink and the green. Well, we know that when we find area, we're finding the area of infinitely many number of rectangles. So let's say I was to draw one of those rectangles, okay, like my ith rectangle. And I want to find the area of infinitely many of these. So by using the definition of a Riemann sum, we want the height of this rectangle in order to find the area of it. So how would you find the height of this rectangle? Where the height is, of course, between the pink and the green curve. Well, I hope you said you're going to take the top curve minus the bottom curve. So in this case, x minus x squared would give me the height of this rectangle. So this leads to area between curves that are perpendicular to the x-axis. So the area A of the region bounded by the curves y equals f of x and y equals g of x, and the line x equals a and x equals b, where f and g are continuous, and f is greater than or equal to g, for all of x in the interval a to b. Then the area is considered to be the integral from a to b of the top curve minus the bottom curve, or in other words, the greater curve minus the lesser curve. And that represents your height of your ith rectangle. So again, top curve minus bottom curve. So let's continue our example. So this is what we have so far. So if I want to find the area of this region, that means I'm going to integrate between the two intersection points that these two curves make. So that would be 0 and 1, which also happens to be the interval I was given. So I want to integrate this height, so x minus x squared, from 0 to 1. Then I can go ahead and use my integration techniques in order to do so. So in this case, it's very simple, just undoing the power rule, adding 1 to the exponent, dividing by the new exponent, evaluating from 1 first, and then you subtract from 0. So you get 1/2 minus 1/3, which then ends up to be 1/6. So area between curves that are perpendicular to the y-axis. So this time, the area A of the region bounded by the curves x equals f of y and x equals g of y. So the difference here is now your functions are in terms of y instead of x. And the lines y equals c and y equals d, where f and g are continuous and f is greater than or equal to g for all y in the interval c to d. Now before I give you the integration for the area perpendicular to the y-axis, let's take a look at the graph. So what I mean by perpendicular to the y-axis is now when you draw your rectangle, you notice that the height of the rectangle is perpendicular to the y-axis. Whereas in my previous example, the rectangle was up and down, so the height of that rectangle was perpendicular to the x-axis. So this time, what I'm doing is I'm going to find this height, but when I find the height of this one, instead of top minus bottom, there's no top or bottom when your rectangle is flipped like this. So this time you're going to do right minus left, the bigger minus the smaller. So that's what you're going to do. You're going to do the right curve minus the left curve when you are in terms of y. So that's very, very important that the functions have to be rewritten in terms of y. So from my previous example, notice that I rewrote the x squared, y equals x squared, as x equals square root y, and y equals x as x equals y. So right minus left. So this time I have the square root of y first minus y. So a couple things to remember when you're doing this is you always need an interval. If you are not given one, then you have to find the intersection points between the two functions. You need to determine whether you will have rectangles perpendicular to the x-axis or the y-axis. Usually they will tell you, but another good way is to either graph it, or if your functions are already written in terms of x versus in terms of y. Before you set up the integral, you must determine which function is on the top versus the bottom or right versus left. And you can do that by either graphing the functions, but of course, if you do not have a graphing calculator and they're not easy to sketch, another option is to choose a value that's in the interval and plug it into the functions, and the greatest value will be your top or your right curve. So let's do some examples. For all of these examples, we're going to calculate the area between the curves. All right, so for our first example, we're going to look at sine x and e to the x from 0 to pi over 2. So if I was to look at the graph of this, the reason why I know it's going to be perpendicular to the x-axis is because, one, when I look at my functions, they're already in terms of x. And two, when I look at the graph, when I want to evaluate from 0 to pi over 2, I have a top curve. The curve that's to the top is the same curve on the top the whole time. And the curve that's on the bottom is the same curve that is on the bottom the whole time. So which curve is on top and which curve is on the bottom? So if you were to plug in, say, 1 into each of these functions, you would get e to the 1, which is 2.7, so on. Plug in 1 for sine, you're going to get a number smaller than 2. So that means my top curve is the e to the x curve, and my bottom curve is the sine x curve. So that means I'm going to do top minus bottom, and I'm going from 0 to pi over 2. Now I can go ahead and integrate this with my integration techniques. So I get e to the x plus cosine x, since the antiderivative of sine x is negative cosine x. Now I'm going to evaluate from 0 to pi over 2. So when I go ahead and plug in pi over 2, I get the following, and then 0. After evaluating and evaluating a little bit more, I get e to the pi over 2 minus 2 as my area between the two curves. And if you had your calculator and really wanted to get the decimal, you would have 2.8105. All right, why didn't you guys try this one on your own? Let's see how we did. All right, so if I was to look at the graph of these two functions, you would notice that the curve that's on the top remains the same curve on the top the whole time, and same with the bottom curve. That means I'm going to integrate in terms of x. I'm going to do top curve minus bottom curve. The top curve is the cube root. The bottom curve is y equals x. And since I was not given an interval, I have to find the intersection points. So doing that either via calculator or setting these equal to each other and solving for x, you would get 0 and 1. So I'm going to go from 0 to 1, top curve minus bottom curve. Going to integrate, evaluate, and simplify. All right, now let's look at these two curves. All right, so if I was to graph these two curves, I would get a graph that looks like this. And when you notice is that they're intersecting 3 times, one here at the 0, at the 1, and at the 2. Now, when you're looking at these graphs, you'll notice from 0 to 1 that the pink curve is on top, but then from 1 to 2, the green curve is on top. So when that happens, you're going to have to set up 2 different integrals. And you're going to have to first evaluate from 0 to 1, and then from 1 to 2, because what curve starts off on the top changes. So I'm going to integrate from the 0 to 1. My top curve is the x cubed. My bottom curve is the 3x squared minus 2x, so I'm subtracting it. Notice you don't want to put parentheses around that whole thing so that you can distribute that negative and not lose a negative. Then you're going to add the integral from 1 to 2, but this time the top curve is the 3x squared minus 2x minus the bottom curve, which is x cubed. So now you're going to go ahead and integrate. Then you're going to have to evaluate for each one. And then after doing some simplifying, you're going to get an area of 0. All right, now let's look at one where we have to go in terms of y. Okay. So for this one, we're going to want to integrate in terms of y. And here are a couple of things to help you know when to integrate in terms of y. First, the functions are already in terms of y, and in this case they are. Second, it is easiest to solve for y. So sometimes one function will be in terms of x, and then the other function will be in terms of y. So you would want to integrate whichever variable it's easiest to solve for in whichever equation. And then the third part is it's easiest to draw a rectangle horizontally. And what that means is if I was to look at this graph, and you'll notice from this x value to this x value, if I was to draw a vertical rectangle, that rectangle is going to, its top curve and its bottom curve is the same function. So if I was to do top minus bottom, the functions would cancel each other out. So that doesn't really work. So I'm going to integrate in terms of y. So I'm going to do right curve minus left curve. So in this case, my right curve is the 2y minus y squared minus the left curve, which is y squared minus 4y. And I'm going to integrate from 0 to 3 because that is where my two graphs intersect in terms of y. So the y values in their intersection points. So I'm going to go ahead, simplify, integrate, evaluate, so I get an area of 9. Well, I hope you enjoyed learning how to integrate area between two curves, and I will see you in class tomorrow. Have a good night.